Good evening,
Sir,
sir.
good evening. Good
Good
evening.
evening, sir.
So, being the coordinator of this Atal online 6 days faculty development program conducted by Institute of Technology, Bhubaneswar. So, it is my responsibility to heartily welcome all the participants and expert to this session. So, before that, I want to introduce the first session, Dr. Priyadarshi Das, and he will deliver the topic computational modeling for dynamic and stability analysis of cracked laminated composite beams, insights into vibration and buckling behavior. So Dr. Priyadarshi Das is working currently as assistant professor in the Department of Civil Engineering at Institute of Innovation and Research, ITER, that is Shiksha Anusandhan, which is deemed to be University of Bhubaneswar. He obtained his PhD in civil engineering from the National Institute of Technology, Rourkela, specializing in structural engineering with a focus on the static and dynamic behavior of structures. His research expertise includes vibration and buckling analysis, structural health monitoring, stability studies, and the application of intelligent computational tools such as fuzzy logic and artificial intelligence in structural science. With over a decade of teaching and research experience, Dr. Das has guided several undergraduate, postgraduate, and doctoral scholars. He has contributed over 30 peer-reviewed journal papers, book chapters, and conference publications. During his active engagement in research, he also served as the convener of the first international conference on advanced technology in material science and engineering. In short, ICAT MSc 2024 successfully organized at ITR Shiksha Anusandhan, deemed to be University of Bhubaneswar. Dr. Das' current research interests include composite and sustainable construction materials, vibration-based damage detection, and AI-assisted structural performance evaluation in the field of civil and material science engineering. So we have today a very great personality with us. So definitely we will gain some knowledge from him. Now I once again welcome our expert, Dr. Das, and request you, sir, to start the session.
Thank you, sir. Thank you for a warm welcome and warm introduction. So, from my diploma days, I have heard about you, and it's my privilege being introduced by you in such a platform. So, let me share my screen, sir. Is it visible, sir?
Yes, yes, it is visible.
Okay. So, it's my privilege to be present a topic here in the faculty development program on revolutionizing the construction with sustainable advanced material that is jointly organized by AICT with Synergy Institute of Technology. I give a big thank to for inviting me to present this topic, and that is computational modeling for dynamic and stability analysis of cracked laminated composite beams, insight into the vibration and buckling behavior. As we know that the composite materials that has been emerged as a cornerstone material in the field of engineering applications, ranging from a spectrum of fields, that is from aerospace to civil engineering, from agriculture, uh, civil infrastructure, mechanical engineering, and by its wide engagement in such fields, it has attract the environmental loads and as well as the different static and dynamic loads, for which the cracks are initiated in the beam and through the propagation, ultimately is responsible for the catastrophic failure of the structure. So that's why it is very important and it is a challenging issue to address the buckling and dynamic behavior of the laminated composites, be it beam or plate or shell. It is a challenging issue to analyze such parameters uh, in the best interest of the design, so that in such wide engagement, these lighter structures can be used smoothly. So now, my overview of the presentation that includes for highlighting the composite, its need and the need for the crack analysis through the material design, and how the data has been analyzed for the vibration and buckling through different methods, that methodological approaches we have been through, and at last providing the concluding insights to this vibration and buckling behavior that has been associated with the composite materials. So what is the why we need the composite materials? The composite materials have been widely engaged in modern engineering due to their tailored structural properties, the inherent capability of the composite, that the inherent capability of the composite, that is combining two structures by maintaining their originality. That means two structures or two different materials have been combined together to form a single material, where individual material will not lose their integrity. This will enhance the performance of the material, also enhance its applicability. So significantly, this motivates to use the composite in widely engaged engineering or applied engineering fields. So we can say that what is the need for composite? It has the improved Taylor properties. So this improved Taylor properties of high strength and stiffness. The high strength and stiffness, so essentially it will reduce the stiffness to weight ratio and strength to weight ratio, that essentially reduces the weight of the structure. So making it a lightweight structure and without losing or without compromising its performances. So that's why it is weight sensitive and cost effective, and that is for high strength to weight ratio. It is low utility cost in the long run, and since it has some that engineering advantages, so it has used in different engineering fields, ranging from the aerospace to civil to mechanical to irrigation, even in sports goods also. So these are some uh, engineering application for the composite materials. Now the real world application of the composites. So these are some examples: that composite bridge in Oxford, this is composite wings and fuselage. It is a very well known thing that the aeroplanes or aircrafts are being made with the composites, and this is the industrial rail made of composites. These are some primarily focused composite uh, materials in the real world application. Now, if I'm going, we are going to the analyze the uh, mechanism of the composite. So the laminated composite are engineered by stacking the laminas or plies. So each oriented in a specific direction. So this facilitates or this imparts the direction dependent stiffness and strength. That means if we are saying that this for the micro mechanics that lamina, the each lamina is placed in a certain direction. In that direction, we can easily calculate the stiffness and strength. So essentially, for the laminate, it has two phases, that is matrix phase and fiber phase. The fiber phase carries the load, whereas the matrix phase transfers the stresses between the fibers so that it will protect them from the environmental loading. The matrix phase protects the fibers from the environmental loading. So this mechanism is clearly explained by Kolar et al. In their research paper where I have taken this picture. So this laminate, the preparation of this laminate, the fabrication of this laminate needs certain temperature and pressure. For that thing, it will and certain certain pressure and temperature so that the bond between the laminates should be uniform. It is very essential to maintain that uniformity to maximize or to get the optimum or the optimal performance of the composite. So, like I said that if a structure is continuously used or widely engaged in such engineering fields, it has the tendency to form the crack or disintegrations. The disintegration, when it is formed inside the structure, it will lead to the catastrophic failure. And on its wide engagement, it will combinedly attract the vibration and loading. If vibration, loading, and buckling happens at the same time, then both intra-ply failure and inter-ply failure will happen. So this will damage the structure as soon as possible, to damage the structure on a quick node basis. So that means both on vibration and buckling, the catastrophic failure will occur sooner than later. So towards this, so pretty research attention are given. Like we see this in this figure that the through analytical solution and numerical solution, addressing the cracks in a composite, laminated composite has gained a wide research attention, where the notable research attention was given to the analytical and numerical both combined. But as you can see that the this numerical and experimental thing, and also the experimental uh, analysis to the laminated composite inculcating the cracks has been got the less attention. So if the numerical models validates through the experimental analysis, that will facilitate the engineer to provide it as a design aid through the construction of or through the application of laminated composites. Now, so based on that, the selection of material is quite again, it is very important. Uh, this this explains the design of material, that explains the key material selection parameters that is grouped in general mechanical and thermal properties. It illustrates or it explains how the material behaves under load through stiffness, strength, its ductility, brittleness, and how the material respond to the temperature, the response to temperature changes, to the thermal expansion and thermal conduction. Overall, we can it will provide a quick guide for the designer. It will provide a quick guide to the designer to compare the material based on the performance requirement for the engineering application or for the engineering design. So it can be better understood when the properties of performance, like if I take the aircraft wing, if the aircraft wing it is not adequately selected through stiffness, strength, toughness, and weight, it will break. That means we can see that if it is too heavy, we need to lower the density. If it is not tough enough, we need to bigger the fracture toughness. The fracture toughness is nothing but that is the material's resistance against the crack propagation. So similarly, if you need the bigger E, if it is not stiff enough, that means optimizing or selecting the materials in such a node that it will arrange all those parameters, that is stiffness, strength, toughness, weight in one alignment so that it can be used in a composite aircraft wing. So again, so if you are going for the material design, that material design, the composition and processing, that will determine the material's microstructure, which in turn governs the property and performance of the structure. But the conflicting thing is that during the material design, a designer or an engineer always encounter two things, that is conflicting properties and conflicting requirements. So what is conflicting properties? The conflicting properties occur when you are improving one parameter that worsen the other parameter. For example, increasing the strength may decrease the ductility. Increasing the strength may decrease the ductility, or increasing the stresses or increasing the stiffness may decrease the toughness. So that is the conflicting property. What is conflicting requirement? This conflicting requirement is at the same time one material needs two unachievable things, or it demands two material properties that is quite difficult to achieve. That means if a material needs uh, it is highly conductive, at the same time it should be highly resistive against heat. So on such circumstances, it is quite difficult to choose a material to used as a structural element. So that's why material design plays an important character where between two distinctive properties, it can be compared against that thermal insulation, thermal conduction, through that stiffness, through that strength, so that material can be used as a structural member, a structural material in different applied engineering fields. So all those things can be quietly achievable through composite matrix, because we are integrating two different materials, two or more different materials into a single materials without losing every material single entity, every properties of the single entity. So now this computational approach for the material design, it describes uh, the entire process of the material design. That computational approach, it will describe the entire process of the material design. So it includes first that we need what are the basic need for the material, what is the basic need for the design. That means is the identification from the need to building the mathematical model to running the simulations, and with the optimization and to select the best material. That means this includes the process from needing the material to selecting the material. So that selection is based on the mathematical performance, how the mathematical model has been governed, and how that mathematical model is simulated for that optimization to selecting the best material for the use. And different approaches have been made for the materials modeling. Different approaches have been made, and these approaches has been from different stages. That is from the atomic level structure, that is uh, density function theory, molecular dynamics, to the macro level electrochemical functions, that is thermochemistry, thermochemistry, phase field theory, to the structural field, that is finite element analysis, finite different analysis, differential quadrature analysis, component mode synthesis, that analysis. So from for the different approach, we are analyzing the composites in different theories, and along with that, the fuzzy logic based application is also there. The fuzzy logic based application, that is essentially a soft computing tool. So we can say that the AI integrated tool may be used, that is data driven. So whatever the data that is needed in the structure, or what is the data that is coming from the structure, that data is trained through a soft computing tool, and that will enhance us to find the best suitable material for the application. Like if we cannot say that always a composite plate or composite material is using in aircraft tooling. Most of the time, it is fiber metal laminated plates are used. So some persons use composite plates, some persons use fiber metal laminated plates. So for the entire structure, for which part it can be used, that material design enables the designer to identify and to um, place those structures for that engineering application. Now, this modeling can be drawn from the electron level to the engineering design. So that essentially uh, illustrates, or this figure essentially illustrates that the multi-scale approach for the composite material design, from the quantum mechanics to the component strength, life and reliability. We can say that from interatomic potential to the interface, stress concentration factors, ply strength, all those things from the electron level to the engineering design we have achieved. So neither multi-scale modeling hierarchy, the multi-scale modeling hierarchy that shows the nanoscale to the material level. So here, if we are taking a case study as the same is carbon nanotubes that are integrated from nanoscale into the fibers, plies, and finally full composite uh, structure that is used in aircraft tooling. So here the material informatics, where this the material innovation infrastructure that highlights that integrates the computational tools, experimental tools, and digital data towards for my societal application that requires or that integrates the clean energy, the human welfare, national security, and the next generation workforce. That means it will enable the future generation, or it enable the workforce that will integrate these ideas or integrate these uh, processes to find the best suitable material for the structure or material for the application. Now the methodological approach towards the crack analysis. So crack laminated composite beam, basically we have analyzed through the numerical modeling and experimental method. Analytical solutions have their own restrictions. That means through analytical solutions, the mathematical formulation that governs the equation that is applicable to only one part. That means only for the limited boundary conditions. Suppose we are going to find the frequency for the cantilever beam. It can be analyzed through the analytical method. But if that boundary condition is changed, or that boundary condition is different from the different structures, it is very complicated to get the frequencies through the analytical solution. Why you are adopting the numerical methods? Because numerical methods are the approximate methods. How the if the approximation is quite higher, or what approximate is quite close to the reality, we get the accurate answer. And these things is validated against the experimental method. Here it is a graphical presentation of the instron. Through instron we are getting the material properties. For the vibration we need the vibration apparatus. For that that is a different thing. For numerical method, it is finite differential method, GQM, that is the Gauss quadrature method, component mode synthesis analysis. This Abacus, ANSYS, MATLAB, Photon, those are the software packages. So we adopted the Abacus finite element software. And the different types of cracks are the open cracks, breathing crack, edge crack, central crack. The crack influence here is the crack that is formed inside the structure, that is a intra-ply failure. And due to that intra-ply failure, the stiffness will be reduced, and since the stiffness is reduced, the frequency will drop. That means frequency analysis, it is a non-destructive tool that if the structure is in intact position, it will And if the structure is in the disintegration position, the disintegrated structure, their frequency will be dropped. From that frequency drop, you can easily analyze that something went wrong with the structure, and somewhere the structure has been disintegrated, and we need to find out. So the frequency is passed through the structure. Where the frequency is obstructed, at that point you can look at the disintegration or that crack. So this can be drawn from the local modeling approaches, that is local flexibility approach or FEM partitioning. So FEM partitioning is quite effective than the local flexibility. And here the fracture mechanics concept that at the crack tip, the stress intensity factor uh, is more. In fracture mechanics, the stress intensity factor that quantifies the stress concentration at a crack tip. So how much stress is concentrated at that point? So if the stress concentration is more, then the failure of the structure is imminent. That means this flexibility matrix will reduce. If the flexibility matrix will reduce, flexibility matrix will increase. If the flexibility matrix is, or the local compliance will increase, that will reduce the stiffness of the structure. If the stiffness of the structure at that region is reduced, it will directly affect to the structure and it leads to the failure of the structure. So for this, we need the crack analysis. Here, the relationship between the stress intensity factor and flexibility that has been formulated here is delta C is the local compliance. So it is local compliance is nothing but the flexibility. U is the strain energy release rate. P is the applied load. For this, we can find the local flexibility as the 2k square by E P square. So now the finite element modeling, where the mesh size, where the crack is occurred, that region, the stress distribution curve will give the flexibility increase rate. For that flexibility increase, we get the reduced stiffness values. So mathematically, this can be presented as this. If K is the stiffness, global stiffness of the structure, so it is the global stiffness, that is the stiffness matrix of the intact structure minus stiffness matrix of the crack, and the local flexibility can be computed through this. So this formulation can be implemented through finite element modeling. So if you are using the Abacus finite element software or ANSYS finite element software, they form that library. You can form a model where the cracks are assigning the cracks are quite easier. But when those models can be formed through MATLAB or Fortran, you need to write the code. For that code, that mathematical presentation, you need this formula to incorporate those formulas to the crack region. Because when a crack is formed inside the structure, it will divide the structure into two different materials or two different things. That means if L is the length of the beam and wherever the crack is formed, then that beam is divided or discretized into two parts, L1 and L2. And at that point, you need to incorporate the crack stiffness value. From that crack stiffness, you can find the entire reduced stiffness of the structure. So this is quite essential for finite element modeling. So here it is the mathematical formula that is useful in engineering form, that is explained, where EI is the intact bending rigidity of the beam, effective bending rigidity of the cracking, then natural frequency, that's nth natural angular frequency of the intact beam, then angular frequency of the crack beam. So we got the relationship as the Wn divided by Wno, that is EI effective by the square root of EI effective by EI. So this formulation will enable that modeling approach to find the what exactly how the severity of the crack is and how it has impacted for the stiffness. So this is a typical laminated composite cracked beam where you can find the non-cracked layer and cracked layer. So basically we have presented here a 4-layer beam where first layer is cracked and the two cracks are formed at L1 and L2. and where the crack depth is A. And all other usual notations describe the geometry and coordinates of the beam. So here the displacement field based on the FSDT, that is fast order shear deformation theory, and here a typical 5 degrees of freedoms are there: u0, v0, w0, theta x and theta y. That means all in 3 directions. The translations are taken, and the rotations are taken in theta x and theta y, and the 5 degrees of freedom for node is taken, and the element stiffness matrix that is governed through this uh, Jacobian transformation, that element stiffness matrix, element geometric stiffness matrix, that is used in the buckling, element mass matrix, that is constant, and the total compliance is, that is the compliance is nothing but the flexibility, that is intact compliance of the intact beam, compliance of the cracked region, and the total flexibility matrix can be governed as a 15 by 15 matrix. So this 15 by 15 matrix can be modeled through Abacus or ANSYS and can be modeled using the MATLAB finite element software. So the governing equations are k minus omega square n equal to 0. That's ke minus lambda kg, that is equal to 0, where omega square and lambda that defines the free vibration and buckling. So this is the simulation process. This flowchart, follow this flowchart to prepare a simulation model in Abacus, where you have to select the model from its library. So basically it is a brick element with C3D20R element. I have taken C3D20R element. C3D8R elements are also there. C3D8R elements, or I have also taken C3D8R elements, C3D20R elements. Then select the model, assign the geometries, that is usual geometries, length, breadth, height. Then input the elastic constants A and G. So it depends upon how you are choosing the elastic constants. I have taken in my research, I have taken the bidirectional fiber, that is quasi-isotropic. So quasi-isotropic means the material is composite, but it behaves like an isotope. So that means E is constant. So whatever the E I have taken, that is E1, E2, E3, all in 3 directions, E are same. Then G, G1, G2, G3, all are same. So in our research, this E and G both are same. So that means if E, G same, it behaves like an isotropic, but actually the material is composite. This is called the quasi-isotropic material. So according to your field, or according to your choice of material, may E1, E2 may be different. In I've seen in so many papers that if they have taken graphite epoxy, they have used hemp epoxy, carbon epoxy. Most of the time, if it is their unidirectional fiber, then E1 is different, E2 is different. So you have to check that thing. Then assign the composite layers. Then define the fiber orientations. What are the fiber orientations should be there? So fiber orientations may be changed or may be constant. Define the boundary conditions. It is clamped, that is fixed beam. It is clamp free, that is a cantilever. It is simply supported. So as per the research, you can define the boundary condition. Then select the mesh dependency. This is very important. Before selecting the mesh size, mesh dependency is the very important. If you are not choosing the mesh dependency, you cannot create the mesh size. So select the mesh dependency, then submit the job for the frequency analysis. If you are doing for the vibration analysis, submit the job for frequency. If you are doing for the buckling analysis, submit the job for the static stability or buckling analysis. Then you get the value. If it is converged, then again go to the procedure for the mesh dependency. Reduce the mesh size or increase the mesh size, then again get the value. And thus in this process, you will get the value or you will get the complete result. So we need to think whether this result is accurate or not. But for that thing, we need the convergence study and comparison study. For the vibration simulation, so this is the way we have developed the beam in Abacus platform, where I have shown here 8-layer laminated beams. And for that 8-layer, it is 0-90 degree. It is in horizontal 0 degree, or vertical it is 90 degree. It is a 0-90 ply. Then here the cracks have been formed, assigned with the cracks. And abacus, there is a special case that we can provide the cracks at different regions. So, and here for that crack region, you got the at where the concentration is higher. But through that mesh size, the mode shapes using abacus. So this is the fast mode of abacus. Sorry, fast mode of vibration uh, generated on the abacus platform. After generating the result, you can find this. That platform will facilitate to generate such kind of field. Where three modes are, the three modes can be three mode shapes of the vibration can be easily identified and easily be realized. This is the fourth mode vibration where it is more like a twisting thing. So if you are getting the bending vibration, mode 1, mode 2, mode 3, those are the bending vibration. If the at mode 4, it seems as though it is the twisting vibration. So the buckling simulation. So we have to place the beam as the vertical. Then this is the mesh size. Also, we'll get the mode shapes for the buckling. This is mode 1, this is mode 2. Now the specimen fabrication, we have used two specimens for glass epoxy and carbon epoxy. So in these two figures, the specimen is fabricated like I said in the earlier slides, where the fibers are placed one after another. So in between that, the matrix is there. So that means the fiber is meant to take the load, meant to carry the load, where the fibers distributed the stresses between the so the matrix distributes the stresses between the fibers to resist or to protect it from the external environmental loading. And this is the diamond cutter, where after curing the plate, the beams have been extracted through this diamond cutter, where this diamond cutter, through continuous pouring of water, will get the desired shape of the beam. So for here, the beam size is 25 mm is the width, 250 mm is the length, and the thickness has been measured through the slide calibers. Here it is 2.6 mm. These are the beams after extraction, after cutting from the diamond cutter. These are the beams with its intact stage, and these are the beams with cracked stage. That means cracks are engineered there. So through a hacksaw, cracks are engineered as per the requirement. So if it is a 8-layer beam, we can engineer the cracks up to 1 layer, 2 layer, 3 layer, 4 layer, and it must be done with a great precision. Otherwise, your sample will be lost. So after extracting the uh, beams or beam samples, it is placed on the instrument to calculate the material properties. That is E, G, then mu, that is Poisson's ratio, Young's modulus, rigidity modulus, Poisson's ratio, all things should be calculated. So here is the schematic diagram for the instrument. Here, the original instrument that has been used to generate or to produce the, to calculate or evaluate the material properties is for the carbon epoxy beam. The similar way, the instrument name is instrument 8862. It's basically used for the tensile testing, buckling testing. So here for the glass epoxy beam is used, and the arrangement is for the buckling. And for that buckling, you can see where the beam is buckled at the middle portion, it is break, and subsequently a graph is generated showing the compressive extension against the compressive load. So we can find the compressive load for the glass epoxy beam or carbon epoxy beam or graphite epoxy beam, whatever the matrix. So uh, this is the arrangement for the vibration testing, where the figure A, that is a FFT analyzer, fast Fourier transform analyzer. It is a channel C analyzer. This is made by Bruel and Kaya. Uh, Figure B, that is the impact hammer, where you will impact the beam for that free vibration, and on the fingertip, the hammer tip, a sensor is there. That sensor will execute that load to the structure, and that is realized through at D, where the accelerometer is there. It is the sensor that is sensing the vibration, and it is transferred that vibration to a digital format to the display unit. That display unit will generate the graphs. So that means whatever the vibration is generated on the structure, that has been captured through that impact hammer, transferred through that accelerometer, and is processed by the channel C FFT analyzer, and is displayed through the computer. So for that display, you need another software, and that software, LabVIEW software. That on that LabVIEW software, the all the graphs can be realized, or the graphs are be reflected based on the different boundary conditions. And there is a arrangement also to fix the beams as per their boundary condition arrangement, whether it is a clamp free, whether it is a clamp, whether it is a simply supported. All the arrangements has been done, and on that arrangement, we need to perform the vibration analysis, and that is effectively captured through LabVIEW. This is the complete setup. So when the vibration results are obtained, now through Abacus, we need the convergence study. So convergence study is essential to capture its physical form. To capture its physical form towards the vibration. So first, a 500 elements division was taken. For this, we have taken the in our Abacus model, we have taken the characters, the vibration. Sorry, we have taken the material parameters and material properties as it is taken by Talekar and Potambakar. In 2020, they have studied the material, whatever the material properties and whatever their boundary conditions, we have, and whatever their ply orientations, we have exactly taken the same parameters, we have exactly taken the same material properties, and we have applied on our model. So first, we got a mesh division of 500 elements, then 1000 elements, then 1500 elements, and then 2000 elements. So we see that after 2000 elements or after 1500 elements, there is not much difference between the results. That means the results are slowly converging. Its physical interpretation is same. So that means if I are taking 2000 elements or 2500 elements, the computational cost will be lower. If it is a 500 elements, maybe at the decimal point it looks like very smaller, but for a frequency range it is quite high. So for the frequency, if you are taking 2000 elements or 2500 elements, the computational cost is lower. For that computational cost, we have also validated our model against a well-established literature. Again, we go for the model validation by taking another literature, another published literature, that is Maiti and Sinha. In 1994, they have published a paper using graphite epoxy, and we have taken the same material characters, same material properties. Again, we have put it to our developed model in Abacus, and we found the present finite element analysis and with the Maiti and Sinha is very little difference between that. Within the 5% is the difference there. The error is within the 5%. So that means our model is validated against two distinctive literatures. One is for Talekar and Potambakar, one is for Maiti and Sinha. That means whatever the model we have developed using Abacus, that model is robust, providing the same result independent of the materials. So now we can take our material, that is glass epoxy or carbon epoxy, we can take our material to produce the new results, because this model or simulation model is validated against two distinctive literatures, well established literatures. And also you can check the years, Talekar and Kotambakar in 2020, for Mike and Sinha is 1994. That means across the years, this model doesn't give any dissatisfactory results. So we have calculated what is the fiber orientation, effect of fiber orientation. The fundamental frequency for the 0 degree fiber orientation, obviously it is more than the other degrees of orientation, that is 15 degrees of orientation, 30 degrees of orientation, 45 degrees of orientation. That means whatever the whatever the fiber orientation we need that the 0 degree fiber orientation, because it will give the maximum frequency than the other fiber oriented frequencies. So here effect of boundary conditions. So CF means clamp free, SS means simply supported, CC means clamp, that is clamp free is nothing but your cantilever, simply supported and then fixed. So as you see from the figure, it can be realized that the cantilever beam shows the very lesser frequency than simply supported beam and a fixed beam, whereas fixed beam executes or exhibits the highest frequency. So in the application part, the designer must think as per the boundary condition whether the design must include a cantilever portion or a fixed portion. So in between that, if it is there, if a simply supported case is there, so accordingly it will provide a design aid for which condition the laminated composite can be used. The lamination layers. So there is a 4-layer layer, 8-layer and 12-layer lamination. As you can see that from 4-layer to 8-layer, there is a significant jump. But 8-layer to 12-layer, the jump is quite insignificant. And in that line, if we calculate from 12-layer to 16-layer, 16-layer to 24-layer, again that jump will be diminished. So a time will come where there will be no jump or no decrement or increment in the frequency. But we have chosen the 8-layer lamination for our research, since we are doing it numerically as well as experimentally for ambient environment conditions. 8-layer is quite sits well with us. That's why you have taken 8-layer beam. So 12-layer beam or 16-layer beam can be taken. 20-layer beam also can be taken, but the curation process or the fabrication process itself, it will take much time. That means for 8-layer beam, the pressure and the temperature, maintaining that pressure and temperature, it was a difficult task. If you are going for the 12-layer beam, it will be more difficult to achieve the uniformity between the two layers. So like I said earlier, if the epoxy, that is the matrix is lost between two layers, that will essentially transpose the stresses between two layers. But the stress distribution should be uniform. If this is not uniform, then obviously the cracks will be formed there. Now this is the effect of the position of the crack. The position of the crack, that means L1, L2, L3, we have taken that for the intact beam at 0.2 L, at 0.4 L, at 0.6 L, and 0.8 L. What are the cracks have been formed? Now, if I take the single crack position, now we can find at which position the crack exhibits the lower frequency or maximum drop. That means from the intact, at which position crack exhibits the maximum drop. So we can realize from the figure that at 0.1 L here, at the 0.1 L, at 0.1 L, that at that position, at the crack depth, it will execute the maximum drop. So again, if we go for the multiple crack analysis, now consider for the two cracks. Here is a single crack. The crack exhibits the maximum drop at 0.1 L. For two cracks, keeping that 0.1 L is constant because that is the critical. Again, the second crack is varied from 0.3 L to 0.9. Now, for that analysis, as what combination at two crack position where the beam will execute or beam will exhibits the greater reduction in the frequencies. So now here you can find at 0.1 L and 0.3 L at that combination will experience the greater crack or the greater reduction of the frequency. Now if you go for the third crack position, that means for the third crack, the crack needs to be stable at 0.1 L and 0.3 L, and the crack must be varied from 0.4 L to 0.9 L. So this is a sequential approach to quantify. This is a sequential approach to describe the crack behavior inside the laminated structure. So in this way, we can identify easily where the disintegration happens, how the structural behavior is affected through the initiation of the crack. The same thing we are adopted for the effect of the crack depth. For a single crack, the crack depth are from 0, that means intact, to 0.125, 0.25, 0.375, 0.5, and 0.625. So we can find at what crack depth the intensity is higher. So keeping that position same, the other crack depths are varied. Like in position at 0.1 L, the crack intensity or the severity of crack is high. So for two crack analysis, 0.1 L is constant and 0.2 L to 0.9 L that is varied. For crack depth also, we are adopting the same method. Be it the frequency analysis, be it the buckling analysis, we are adopting the same method. But this sequential approach enables to identify the crack severity and to identify how much crack severity is not challenging the structure. That means at what depth, if a crack is there, it can be used as a structural element, and at what depth, a crack severity is so much that the structure need to be replaced or need to be addressed. So this sequential approach enables the designer to effectively verify, to effectively analyze the composite structure. So effect of the boundary conditions for the buckling load, in the same way it has been performed. Now effect of the crack position, both in the same way. For the vibration analysis and buckling analysis, both are the same way. Here, since it is buckling, we have find the maximum reduction happens at the 0.5 L, and for the second crack, 0.5 L is the constant. For vibration analysis, at the 0.1 L, that is the cantilever beam, 0.1 L is the critical position. Here we are finding for buckling, 0.5 L is the critical position. And for the two crack, you can find there 0.5 L and 0.1 L is the critical. So similarly, if it is 3 crack, 4 crack, so there is a pattern. Through that pattern, we can analyze the number of cracks in an element. So this is the effect of crack depth. The same way, the same pattern, it has been calculated. Effect of crack depth for the single crack, effect of crack depth for the double crack. So all these things I have presented the for glass epoxy, and also we are having the values for the buckling epoxy. Sorry, we are having the value for the carbon epoxy. So these are the concluding remarks that the computational modeling framework that captures the dynamic and static stability behavior, the cracked laminated composite beams that offers the accurate insights to both vibration characteristics and buckling performance or static stability performances. This research or through this research we can demonstrate, or we can reveal, or we can clearly explain the crack severity and crack behavior with respect to the laminate on laminate configuration and the mode shapes critical buckling loads, both can be realized. And the main thing is that through abacus, it is independent of the global degrees of freedom. That is, in the beginning, I have shown you the 5 degrees of freedoms are there. So 5 degrees of freedoms, you can model it in MATLAB or Fortran, in ANSYS also. But in abacus, that is, the model is independent of the global degrees of freedom. That means if you are taken 10 degrees of freedom, 15 degrees of freedom, it is independent of that. Irrespective of the global degree of freedom, it will produce the results. Definitely, the number of degree of freedoms, if it is increases, the accuracy will increase. But abacus is such a software that it will independent of that thing, independent of that degrees of freedom, but it will provide the accurate results. If you can compare the abacus results with the ANSYS results and MATLAB results, there is not much difference between abacus and MATLAB also. Within 5 to 6% deviation is happening. So overall, these things the contributes the design optimization of the safety evaluation of the composites structures, paving the way for the future research. Research on composite. So these are some publications I have published, and I have taken all those materials, all those. You can follow these literature, also follow these publications, the better understanding. Thank you. Any questions?
Good evening, sir. A question actually. Hello, am I audible, sir?
Actually, two sounds are there, so it is quite difficult for me to understand.
Hello.
ତା ସାଇଡରେ ଯାଇ କଲେ ହବ।
Hello.
Suraj sir?
Yes, sir. Am I audible, sir?
Haan, you are audible.
Okay, sir. Very nice work, sir. Many congratulations to this work actually. So I have questions actually. Can I? Sir, actually, the laminate that composite that we have taken, first of all, the E value, that you have told isotropic throughout, isn't it, sir? In all directions. Am I right, sir?
I could not get you. The composite I have taken.
That the composite, the experimental, composite beam you have taken in the numerical modeling, you have taken E value same for all 3 directions, isn't it, sir? Am I right?
Yes.
So actually, in practical case, it is not exactly true. So how the experimental values are validated in the numerical modeling, even though you have taken different E value in all 3 or 4
No. Actually, I told that it is a quasi-isotropic material. The quasi-isotropic materials mean the materials are bidirectional. So
Yes,
whatever the material I have taken, that is glass fiber or carbon fiber, those are bidirectional. So if you cut the material in either 0-degree direction or 90-degree direction, and if you going for the tensile testing for the 0-degree direction, it will give the same result as the 90-degree of direction. That means experimentally it is also verified that for quasi-isotropic material, you will get the isotropic results, but the material is composite.
Okay, sir. So thing is that yes, for 0-degree and 90-degree it is okay, and that you have taken 0-degree, 5-degree, 30-degree also the laminates in your numerical modeling.
Yes.
So how it will be validated again? And again, another thing, perpendicular to the plate, that E value is also you are not taking the same as it is from X and Y directions.
No. I have taken bidirectional fibers. For bidirectional fibers, all directions are E are same. If you are taking unidirectional fibers, then there is 2 values. E1 value and E2 values. In stone, it will give 2 values there.
Okay.
Even
Okay, sir.
in many literatures, if you are taken for the suppose say Kissa, the Kissa is a very good eminent person on this composite analysis. He has taken always taken graphite epoxy. For the graphite epoxy, E1 is different, E2 is different. Because
Yes.
E1, E2 both are unidirectional. Because graphite epoxy they have taken for the unidirectional fiber. I have taken the fiber as the bidirectional fiber. So this is the woven one, like this.
I understand, sir. Yes.
This is the woven one. If it is a woven fiber, you will always get the value for E1, E2 both are same in same direction. That means E1 value, E2 value, E3 value all are same. Even
E3
if
value,
you go
E3
for
value,
the
E3 value, which is perpendicular to the plane of the laminate that I am talking about, that also you are considered the same as E1 and E2, sir.
yes. Because if you go for the rule of mixture, that rule of mixture is also give you the same value. Without much deviation, you can try.
Sure.
So
So,
rule of mixture, you have to generate, you have to produce the beam, fabricate the beam, and after fabrication, you have to burn it. Then the residual at that point, applying the rule of mixture, you will find the fiber values, and those fiber values when you are calculating for E1, E2, E3 will govern the same result.
okay,
So
okay.
through rule of mixture, you are getting the same result, and as well as this instant, which is a very high precision data measurement value, that will also give the same result. I have also conducted the both results on that.
And sir, the different angles that you have taken in the numerical modeling, 0 degree, 5 degree, 30 degree.
That is for the computational analysis.
Yes, sir.
Computational modeling we have taken. Let me show you. That is for the computational analysis.
The table that you have left side, I think.
Here. So you can find there 0 degree, 90 degree positions are there. Here.
Yes.
In the first figure.
Yes, sir.
If the figure, the step like figures are there.
Yes, sir.
At that point, you can apply any direction of fibers there. So you can apply for the 90 degree, you can apply for the 0 degree, 15 degree, 7 degree also, 22.5 degree also.
So
For
whenever you
numerical
are
analysis, it is quite easy to apply any fiber, any degree of fiber of orientation. But in practical, they will govern the same. That means whatever the value you are getting for the 0 degree, that's the same value you are getting for the 90 degree. Whatever the value you are getting for the 30 degree, the same value you are getting for the 60 degree. Like
yes,
that.
sir. Yes, sir. That actually I want to know whether for 0 degree, 90 degree it's okay. When you compare with 0 degree and 30 degree, then the
Yes.
E value will be going to change, I think, for both orthogonal directions.
E value definitely change. Obviously, E value will change. Or in orthogonal direction, E value will change. In every direction, E value will change.
So then how can we validate the results with the experimental one? Because that is totally E value is different and we are getting the E value same for both orthogonal direction in case of 30 degree ply or 30 degree laminates.
Now, for a continuation of research, whatever the value we got for that particular beam, we have taken that E value throughout. If we go for the 30 degree value, 30 degree E value is different. 15 degrees E value is different. But we got the comparative value as the whatever the value got for the quasi-isotropic value. That is for the 0 degree and 90 degree. We adopted the same value throughout the experiment and throughout the analysis.
Okay.
So for that thing, and again also if those 15 degrees values and 30 degrees value, if we are going for the we're going for find the E values, that will make a more difference. That will make that 0 degree fiber is more prominent than the
Yes.
other values.
Yes,
Anyway, they will govern the lesser frequencies.
okay.
In 0 degree, as compared to the 0 degree fiber orientation, 30 degree orientation, 15 degree orientation, 45 degree orientation, they'll govern the lesser values. Actually, I have calculated the 45 degree. I have not calculated the 30 degree and 15 degree. I have calculated the 45 degree.
Okay, sir. Sir, actually, one more doubt, sir. Actually,
Yes.
with the interlayer, how many layers that 1, 2, 3, 4, 5, 6, 7, 8, 8 number of layers you have taken, and
Yes.
can what is the interaction that you have taken in between the layers? Interaction, the that I'm talking about the bond whether it is you have considered rigid or any
It's a rigid bond.
rigid
It's a
bond.
rigid bond, and the failure is the brittle failure. It's a rigid
So
bond, and the failure is the brittle failure.
So in your numerical modeling, you have taken the rigid bond. That means embedded one.
No, I have never taken the rigid bond there. There is no option for that bond. But whatever I am telling the answer on the point of view fabrication. Here, the lamination modeling is there. That modeling is for how many layers it will govern how many layers it will prepare the model. So it has prepared the layer for 8 models. So there is no such options to provide the bond is rigid or not. They have not, the model is not asking about the bonds, because
That
only
means
it has been worked through that governing equation.
so
But
we are modeling the laminas one by one, isn't it, or at a
yes,
time?
no,
So
one by one.
if we are getting one by one
Yes.
over the other, then we have to give some interaction property in between the plates.
No, there is no such option for interaction properties.
That means we have to take this rigid one.
You have to take this rigid one. That's why we are getting the different values from the numerical one to experimental one.
So
We are not getting the exact values.
and the analysis has been gone up to what extent, whether up to breaking of that one, have you done it, or some very little that it will not go up to its elastic limit or something like that? If you have gone nonlinear property up to that, then the
Yes.
analysis, the vibration analysis, if you have conducted by any chance at any point, whether that reaches its elastic point or it has not gone its elastic point. Because if it is gone to elastic point, the bond failure, as you have taken as a rigid point, then that's not a problem. But whenever you are going for failure analysis up to the vibration failure analysis, then can we have the result difference in between the experiment and the numerical modeling?
Yes. There is very little difference. Actually, that error is within the 5%. Initially, it was more, but when the pressure and the temperature, it is combinedly, it is in a controlled way. The results are within the error limit. That is within the 5%.
If you go,
Whatever the result we got from the numerical models, though
if you go
sometimes we got
the
the exact results from the experimental one, but sometimes it is debit, but we got the results.
So if you go the analysis in between the elastic range, then I think the E value will not will not affect any experimental and numerical results actually. And if you go beyond elastic limit, I think it may difference. It will give difference result in between the numerical and experimental results. Am I right, sir?
Yes. That is correct.
Okay, sir. Thank you so much, sir. Thank you so much.
Thank you.
So any other participants have any question? Participants are requested, if you have any question, you can discuss with our expert. Sir, our expert has finished the session, and
Yes, sir.
during the presentation, if anyone has any question to put, so now you can clear your doubts. Otherwise,
Another question I have, can I ask, sir?
Yes, definitely.
Sir, the tensile properties of matrix that you have taken, whether it has been already purchased one, you have prepared the lamina, sir?
No, I prepared the lamina.
So matrix and fibers, we have mixed it.
Yes.
So what is the tensile properties of matrix? Whether it is very much lesser than the tensile properties of the fiber?
No. It is not very much.
Okay.
Actually, we have calculated through rule of mixture, and we have calculated through instant. Actually, instant facilitated those things. That's why it's a very precision data line.
Okay.
Instant facilitated those things. We can verify those. So many papers are published through that instant.
Okay, sir. Okay. Thank you so much. Thank you.
Okay.
So any other participants? Any other participants have any question to ask? No more question? So we can conclude this session. Participants are requested to clear their doubts during the presentation if they have. Otherwise, we will conclude this program now. Shall I go for shall I conclude this program? Participants?
Yes, sir. Thank you.
Okay. So
Shall I stop the presentation here?
before that, this is my duty to close this session. So it was a very nice presentation by Dr. Priyadarshi Das. And again, we'll hear from him on, I think you have another session on day 5. That means tomorrow also we have another session. And also that was a very nice topic. That is a very nice topic. So your presentation was excellent, sir. And number of participants were also very good numbers. And also the topic presented by you will definitely help them in their research work, because these are the recent trends. So I again thank you, sir, for your valuable time and valuable presentation, excellent presentation. So with your kind permission, we want to close this session.
Good night, sir.
Good night. Good night. Good night. And all the participants are requested to stay, because our next session will start at exactly 7:30, which will be delivered by again our expert, Dr. Venkatesh Kumar R. Kodur, overseas expert. So participants, please join exactly at 7:30. For this, we are concluding this session. Thank you, sir.